Welcome to this class, and in the last classes we have discussed about the field line microscopy, atom probe tomography, field desorption microscopy, and what are the instrumentation, then the basics related to the field of operation, what are the parameters which are important to reconstruct the needle specimen as equivalent to as it is present in the tip specimen. Okay, so just to replicate the exact the atomic structure, what are the parameters and the influence of those parameters on the reconstruction. Now in this class we will start with the sample preparation, which is a very important for doing the experiment. Okay, so sample preparation. So we know that the sample preparation, it is a very crucial thing where the sample should be optimum enough so that your atoms get polarized at a definite voltage, and so that they can field evaporate. Fine. And the sample preparation, usually there are some conditions for the needle specimen. Your tip dimension or the radius of curvature should be 50 to 150 nanometers. Okay, so it is the optimum range where the radius of curvature should be maintained. Okay, and if there is a larger radius, larger r, then what will happen is it is very difficult for the atom to polarize and get ionized. Okay, so you need if it is a large r, then you need to require a higher voltage to induce the field evaporation such that locally the electric field lines are concentrated enough that these atoms get polarized and ionized and accelerated. Okay, so you need the higher voltage. If it is a very small radius, then your electric field distribution will be very complex and the ion trajectories may distort. Okay, this will have a direct implication on the reconstruction or the of the needle specimen. So the optimum radius of curvature should be between 15 to 150 nanometers or up to 100 nanometers. Okay, the second condition for the needle specimen. So you have a sharp needle. The second condition for the needle specimen is the surface should be smooth. It should be smooth. Okay, means free from any protrusions, grooves and cracks. Okay, so because these protrusions, grooves and cracks, it might possible that the needle specimen will get fracture very easily, so the yield will be very small. Correct. And usually in the reconstruction, whatever the reconstruction we are doing, it is based on the assumption that the tip surface is actually a hemispherical cap. Based on this we are doing reconstruction. So what is the reconstruction? By the reverse projection model. Okay, so your reconstruction is based on the assumption that your tip surface is hemispherical cap. Any deviation from the hemispherical cap, it might lead to the artifacts in the reconstruction. Okay, it may be due to the geometrical discontinuities, stress concentrations. It may arise to the stress concentration such as crack tips or the grooves or the protrusions. Okay, this generates the artifact. The third condition is the tip surface should be of circular cross section. Okay, we have assumed that these are hemisphere and there is a circular cross section, truncated shape. Correct, but if it is not a circular cross section, it might possible that the electric field distribution is very erratic. Okay, this may lead to the inhomogeneous field evaporation from the needle specimen. Okay, so then you will not exactly replicate the needle specimen during the reconstruction. Okay, fourth is the feature of interest. The feature of interest should be within the 100 to 200 nanometers. Okay, so if you are a needle specimen, if you have a certain precipitate, that precipitate should be between 100 to 200 nanometer distance. Okay, this is the one more condition. Fifth condition is the sufficient specimen length. Specimen length. Okay, and also the absence of secondary tips. Okay, so I will go through the sample preparation by focused ion beam or the electropolishing, but before that I need to just discuss about this secondary tip. Usually what will happen during the sample preparation, if there is your main needle specimen, it might possible that there will be a small protrusion, development of protrusion on the sample surface. So during field evaporation, it might possible that your voltage is enough that there will be a field evaporation from these tips. So you will get the extra ions which are actually not from the exact specimen surface which we want. So it will generate a wrong reconstruction or the artifacts in the sample. Okay, and the sixth is the appropriate shank angle. Appropriate shank angle. This we will discuss it during the reconstruction. Okay, so these are the 6 conditions which are very important for a optimum specimen for the needle specimen for the atom probe tomography or the field ionized microscopy. So now we will go to some of the basic polishing methods. Some of the basic polishing methods. The most common method which was used, now also it has been used, it is the electropolishing. Electropolishing. Okay, this is the most conventional method, and the property of the material should be having a good electrical conductivity, and it is suitable for electrochemical cell. Okay, and the material, so this electropolishing, it is nothing but you have a rectangular blanks, this we call as a blanks of some mm size. Then by electropolishing, actually you can thin down this specimen to a needle specimen by removal of this material. Okay, so actually you are doing the removal of the material is removed by electropolishing from the surface of the specimen. Okay, or the protruding parts of a surface profile is dissolved. Okay, so what is the basic to the electropolishing? This is a very basic thing where what we do is simply we need a DC power supply which applies a positive charge to the specimen, which acts as a cell anode. Okay, and this particular sample or the specimen is immersed in an electrolyte, liquid electrolyte. Okay, and together with a cathode. Okay, so basically with this process, when you apply the voltage, there will be a passage of current across this specimen, anode, electrolyte and the cathode. Then the specimen gets started dissolving. Okay, so if you see the schematically, you can have a bathtub. Okay, you have a bathtub, you have a specimen. Okay, you have a cathode. This is cathode, this is anode. Okay, and this is connected to a negative, positive. Okay, so just wait. Okay. Okay, so basically if you see this, it is a very simple cell which is having a container, okay, which contains electrolyte. Okay, you have a cathode, you have an anode which is a specimen, which is a cathode. Then this particular anode is connected to positive, cathode is connected to negative, correct? And this is a specimen, and it is dipped into the electrolyte. Okay, when you pass the current, the electrons will travel along in this direction, and the electrons will travel in this direction towards the positive. Correct? So with this process, what will happen is at the surface of the specimen, the metal gets converted to metal ions, and these metal ions starts moving towards the cathode. Okay, and whatever the electrolyte or the acid which are used, it moves towards the anode. Okay, so at cathode a reduction reaction happens. And at anode where a reduction reaction happens, where usually the hydrogen gas evolves. Okay, so if you magnify this particular region, assuming that this is the surface of the specimen, then usually the metal will dissolve as Me plus ions into the electrolyte, so that it will be there will be a dissolution of the specimen. Okay, and the electrons will travel towards the metal surface or the specimen surface, where it may form oxygen or hydrogen gas, and it gets out to the electrochemical cell. So in this way, you are actually, by time you are dissolving the specimen in the electrolyte, so that your specimen will be removed and it will be converted to a sharp needle. Okay, so usually during the etching process, there are 3 regions, or during the electropolishing. Okay, so this is your current density. Okay, and this is the specimen voltage applied. Okay, volts. Okay, so here we can mark 4 positions A, B, C and D. Okay, so the best polishing conditions happens at B to C. Okay, this is the optimum condition where the current density doesn't change drastically with the increase in the voltage. This is the optimum condition. While in A, B, usually the current density changes drastically in the voltage, so usually it will happen etching. And in C to D, it happens pitting. Okay, so your voltage should be such that the optimal condition, it should be in the range of optimal condition between the B and C. Okay, and the shape of this particular curve depends on the material, electrolyte used, temperature of electropolishing and the geometry of cell. Okay, so these are the 4 conditions which can change the shape of this particular curve. Okay? And in this B to C position where the current density doesn't change with the voltage much, that is the optimum condition. Now, what are the steps to prepare for the for electropolishing? The first is, if you have a bulk material of larger dimension, bulk material of the larger dimension, this bulk material has to be converted to blanks. Blanks means these are very small rectangular slabs of few dimensions with a length of in centimeters. Okay, in few centimeters. So the cross section is around few mm. So these are called blanks, which can be made by either slow speed saw, by using slow speed saws, or cutting with the EDM cutting machines. Okay, so the cross section of this particular blanks is around 0.3 mm square. Okay, and the length is few centimeters. It's about 225 mm, around 2.5 centimeters long. Okay, so you can use the precision saw, slow speed saw, for cutting the blanks from the bulk samples. Okay, so these blanks, individual blanks, are used as the anode in an electrochemical cell, where the material is removed from the tip surface, from the cross section, so that it will become a sharp needle. Okay, so in earlier days, the most popular method which is used for electropolishing is a multi-step process. Okay, in this multi-step process, the first step is rough polishing, and the second step is fine polishing. Okay, rough polishing, this is nothing but it is due to we can say it as a formation of neck. Fine polishing, after the neck formation, it is sharpened to a needle specimen, to a tip. Okay, so based on the material, different types of electrolytes can be used. Okay, and for rough and fine polishing, we can also change the concentration levels of the electrolyte. Based on the concentration levels, you can either actually do the rough polishing or fine polishing. Okay, so this in the multi-step process, these two are the two methods which is used. Okay, what is this rough polishing? Usually these are called as a double layer method. Double layer method. Okay, so here, so this is just a general it is showing the blanks which are made from the bulk sample. Okay, you can see these blanks are nothing but a rectangular cross section rods of that particular sample, which is having around 0.3 mm square cross section, and the length is around 25 mm. Okay, so these are the blanks. Now the double layer method is, this is called double layer method. In this method, usually the first step is rough polishing and the second step is fine polishing. Okay, so in rough polishing what we do is, this is a one blank. Okay, so here, and this acts as a anode and this is a cathode. This is your electrolyte and this is your inert. So in this, the specimen means the blank is repeatedly dipped into the layer of an electrolyte which is at the top of, which is placed on the top of an inert layer. Okay, and this inert layer it is nothing but a perfluorinated polyether, which is also called PFPE. Okay, so in this, the blank is repeatedly dipped into a layer of electrolyte on the top of an inert liquid. Okay, with this, and the current is the DC voltage. The DC voltage is applied simultaneously. So it is moved up and down. Okay, this up and down motion allows the control over the taper, which forms as a necked region. Okay, so this is called the neck region, and you can see that the material is been removed from this neck region. Okay, so this is done until these blanks become thin enough so that it will be in the few micron level. Fine. Once these are thin enough, it might possible that they can break away. Okay, so this can be monitored by the current. Okay, so the polishing will be continuing when the current is still showing some value. When the current becomes zero, it means that it is near to the breakaway of these flanks or the blanks. Correct. Then once the sample cross section becomes a few micrometer cross square, then what is done is the second method is followed, which is called fine polishing. In fine polishing, what we do is we don't use any, so inert layer is not used, the complete electrolyte is used. Okay, with a different concentration. This is your cathode, this is your anode. Okay, so this polishing is again repeated by up and down motion of that particular specimen, and it is done until these two the blank separates in two pieces, and the cross section of this particular where the necking has formed, it is in few nanometer range, nanometer square area. Okay, so this is called final polishing, and this final polishing also removes the damage on the surface, protrusions. Okay, so this is how we prepare a needle specimen, and the needle specimen will be sharpened, which is approximately of radius between the 50 to 150 nanometers. Okay, so this is how electropolishing is done. So this is a double layer method. But now this is the old process which we make nowadays. The rough polishing, usually the first step, rough polishing, is directly carried out in the in the electrolytic cell, where there is no inert layer. It is just a beaker. You are putting a beaker and you are putting an electrolyte, and the rough polishing is done directly in the complete electrolyte. Okay, then okay, so it means that you have, so once this rough polishing is done in this particular, so once this rough polishing is done, then you will have a needle specimen. You have a needle specimen which is having a few micrometer square area. Okay, this particular needle specimen again goes to a second step where we use a rig. Okay, so in which the electrolyte is suspended by using a loop of that particular cathode or the cathode. Okay, so this is the second step. What after preparation of a needle specimen by using the electrochemical cell. Okay, this rig is nothing but you have a platinum wire, and this particular wire is bent in such a way that it looks like a, at the end it looks like a circle, or you can tell as a wire loop, and at this loop, due to the surface tension, actually you can actually deposit an electrolyte. Okay, so this is your loop of that platinum wire, and there is an electrolyte, which is held on that particular loop due to the surface tension. Fine, and your needle specimen, which was prepared previously by the rough polishing in an electrolyte, is kept into this particular loop, and it moves up and down. And while moving this up and down, what you see, there will be a polishing of this particular needle, and this micrometer square needle converts to the some few nanometer square cross section needle. Okay, so this is the fine polishing. This is your fine polishing. And this method now it is used most popularly everywhere in several labs, where the rough polishing is done by simply an electrochemical cell with the electrolyte. Once these needle specimens become sharp enough in micrometer square range, the cross section, then you can prepare a loop by the platinum wire, and due to the surface tension effect, you can suspend the electrolyte on this particular loop. And by this arrangement, you can do up and down movement into this particular electrolyte, so that until that this particular tip surface becomes in a few nanometer square cross sectional area, and the DC power supply is continuously applied across these needle specimen. Fine. So usually it is not only in vertical direction, you can actually also do this particular thing in horizontal direction. And the electropolishing, if you put up a microscope, optical microscope, high resolution microscope, actually the thinness of this needle specimen can be watched lively. Okay, so this is the basic thing which usually now people are carrying out for the electropolishing. Okay, so here the only difference is the needle specimen is repeatedly pushed through the loop. This is your loop, this is your platinum wire, correct, to the loop that holds the drop in the electrolyte due to the surface tension effect, and the tip becomes sufficiently sharp. So this is an optical image of a sharp tip which is having a few nanometer square cross section. Okay, sometimes as this is a destructive technique, the field evaporation, once your tip surface becomes fractured or the voltage has increased enough that the tip becomes blunt, then this method, the final polishing method, can also be used to make this particular tip sharp enough for further analysis. Okay, so what we need for this purpose? We need a power source, we need some beakers which can hold the electrolyte, we need some electrolyte which depends upon the material to be polished. You need a inert material, usually we have a platinum wire, okay, and the platinum wire which is made into the loop, and there is a binocular or optical microscope. These are the four important things which we need, 4 to 5 important things which we need for a electropolishing to be done. The only disadvantage, with the electropolishing is you cannot prepare site specific. This is like for example, if you want to do a field evaporation across a grain boundary, across interfaces which controls your overall material properties, you cannot prepare the site specific methods by electropolishing samples. Okay, so by heat and trial only you can get, somehow we can do we can prepare these samples from the grain boundaries or interfaces. Fine. So typically, as I told you, this is a setup where it is in the ISC. Okay, so this is your microscope, optical microscope, and this particular is that small fine polishing electrochemical cell. Okay, so here you can see that this particular if you zoom this particular region, okay, you have a crocodile clip. This is a crocodile clip which is holding the specimens here. This is called specimen, which is having a several tips. Okay, and this particular wire is called platinum wire, and you can see that there is a loop, and you can see there is an electrolyte which is suspended on the loop, and the crocodile lock pin is moved up and down such that these tips will go into the electrolyte which is suspended on the loop and get electropolished, and a DC voltage is applied continuously across the electrolyte and the platinum inert wire. Okay, so this is how usually we'll do the electropolishing for the specimens, and electrolyte depends upon the material which is investigated. Correct. So this is the most versatile method for preparation of atom probe needles or the field ion microscopy needles, but only disadvantage is that we cannot make site specific needles wherever the precipitates or interfaces are needed. Okay, so with this I will end this class now. In the next class, what we discuss is how to prepare a site specific methods. Recently there is a huge development in focused ion beam microscopy, where you can use heavy liquid elements or ions which can be focused through lenses, and those heavy ions can actually used to remove the material or to trench the material in such a way that you can actually make the needle shaped specimen, site specific. Okay, so we'll meet in the next class with the second type of sample preparation method. Thank you.